We are in section 11.6, absolute convergence and the ratio and root test. Given any series, the sum of a sub n, we can consider the corresponding series, which is going to be the absolute value of n, taking that sum of all those. And this would be the same as saying the absolute value of a1 plus the absolute value of a2 plus the absolute value of a3, and so on, whose terms are absolute values of the terms of the original series. So the box right below, I'm going to give it a few stars. This says a series of a sub n is called absolute convergent. So vocab word we need to know. If the series of absolute values, the sum of the absolute value of a sub n is convergent. And so from this, we can say that if we have the sum of the absolute value of a sub n, if that converges, this implies that the sum of a sub n will also converge. And then it also says a series, the sum of a sub n, is called conditionally convergent if it is convergent but not absolutely convergent. And so for this, we would have the sum of the absolute value of a sub n is going to diverge, but the sum of the series a sub n will converge. In the case that's not listed on here, is going to be divergent. So this is going to be diverges if the sum of the absolute value of a sub n and the sum of a sub n both diverge. So at the top of the next page, we have a theorem that says if a series a sub n is absolutely convergent, then it is convergent. And then right below this, we have the ratio test, which is another test that we're able to use for certain cases. So the ratio test says if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n equals L, where L is less than 1, then the series from n equals 1 to infinity of a sub n is absolutely convergent and therefore also convergent. Number 2 says that if we have the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is equal to L, and this time L is greater than 1, or if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n equals infinity, then the series from n equals 1 to infinity of a sub n is going to be divergent. 3 says if the limit as n approaches infinity of a sub n plus 1 over a sub n is equal to 1, then the ratio test is inclusive. That is, no conclusion can be drawn about the convergence or divergence of the series of a sub n. So we'd have to look at some other tests to use in this case. So definitely another test that we need to know and know those conditions. The example right below the ratio test says determine whether the series is absolutely convergent, conditionally convergent, or divergent. And we're going to go ahead and make sure that our series says the sum from n equals 1 to infinity of negative 1 to the nth over n. And so for this problem, our a sub n value is equal to that negative 1 to the nth all over n. And we're going to go ahead and try that ratio test. And the ratio test says that we're going to be looking at the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And so we have a sub n written down. Let's talk about a sub n plus 1, which is instead of the nth term, it's the n plus 1 term. So we have negative 1 to the n plus 1 divided by n plus 1. And so we're going to have the limit as n approaches infinity of the absolute value of a sub n plus 1, which is negative 1 to the n plus 1, all over n plus 1. And instead of dividing by a sub n, I'm going to multiply by that reciprocal, same idea, algebraically and mathematically. So we have n over negative 1 to the n power. Since we are dealing with absolute values, you can think of those negative 1s as not mattering, since the absolute value of negative 1 would be 1, and that doesn't change anything. So we have the limit as n approaches infinity of n over n plus 1. And again, in absolute values. So evaluating this limit as n approaches infinity, we would have infinity over infinity, which is indeterminate. So the way that we learned to deal with this back in Calc 1 was to multiply both the top and the bottom by that power in the denominator. And so I'm going to multiply both top and bottom by 1 over n. So this is now going to become the limit as n approaches infinity of the absolute value of 1 over 1 plus 1 over n. And as n is approaching infinity, that means this 1 over n is going to be 1 over infinity, or practically 0. And so this is going to be limit as n approaches infinity of 1 over 1 plus 1 over n would just be equal to 1. And so looking back at our ratio test, you'll notice that if it does equal 1, it's inclusive, which means we can't draw any conclusion from it. So no conclusion can be drawn. So pretty much this test doesn't work for this case. So we need to think about this in another way. I do notice that because it's -1 to a power, we are dealing with an alternating series. So I'm going to assume that because it's alternating, I'm going to try to look at the alternating series test. So the first thing was that the sum from n equals 1 to infinity of the absolute value of a sub n, which is going to be the sum from n equals 1 to infinity of 1 over n. This diverges because it's harmonic. So this is a harmonic series. And by definition, it diverges. And then we also are going to look at the sum from n equals 1 to infinity of a sub n, which is the sum from n equals 1 to infinity of -1 to the nth power over n, which again is alternating. And to use that alternating series test, we need to look at b sub n. And b sub n in this case is just 1 over n. And it would be greater than 0 for all n. So check, that's the first thing. The other thing is that it needs to be decreasing. So b sub n is decreasing because as you increase n, those terms are going to get smaller and smaller and smaller. And then the second thing is going to be the limit as n approaches infinity of 1 over n is equal to 0. So that's our other thing that we need to check. And therefore we can say, so therefore the sum from n equals 1 to infinity of a sub n converges. Again, make sure to state what test you used. So this is by the alternating series test. So since we know that this a sub n is going to converge, however, our absolute value of a sub n diverges, we can say that therefore the sum from n equals 1 to infinity of -1 to the nth power over n is conditionally convergent. Which would be our final answer. So we have another example right below this that I'm going to go ahead and circle, and we'll look at that one together in class. Then we have another test here. The next test is called the root test. And this is if the limit as n approaches infinity of the nth root of the absolute value of a sub n is equal to L, and L is less than 1, then the series from n equals 1 to infinity of a sub n is absolutely convergent. Therefore, it is also convergent. So 2 says that if the limit as n approaches infinity of the nth root of the absolute value of a sub n equals L, and L is greater than 1, or the limit as n approaches infinity of the nth root of the absolute value of n equals infinity, then the series of a sub n is going to be divergent. And then the third case is that if it equals 1, that nth root of the absolute value of a sub n as you take the limit as n approaches infinity equals 1, the root test is inclusive and we can't use it. So we need to think of another test to use. So the example right below says determine whether the series is absolutely convergent, conditionally convergent, or divergent. So the example right below says determine whether the series is absolutely convergent, conditionally convergent, or divergent. So again, in order to look at this, our series for part A is going to be n equals 1 to infinity of negative 2 to the nth power n to the nth power. What I noticed with this problem is that everything is raised to an nth power. So dealing with an nth root would be nice. So I'm going to go ahead and write down that a sub n is equal to negative 2 to the nth power all over n to the nth power. And so the absolute value of a sub n would be the absolute value of negative 2 to the nth power over n to the nth power. And so this would be able to be the same thing as, since the negative wouldn't matter since we're dealing with absolute values, it's going to be 2 to the nth over n to the nth, or rewriting this as the absolute value of 2 over n to the nth power. And we also have rules where you're able to pull out that exponent of n outside that absolute value. So I'm going to consider the root test, which is listed right up above, and this is going to be the limit as n approaches infinity of the nth root of the absolute value of a sub n. And so for us, for this problem, we have the limit as n approaches infinity of the nth root of a sub n, and a sub n is going to be the absolute value of 2 over n to the nth power, which simplifies to the limit as n approaches infinity, which simplifies to just 2 over n, which would equal 0 as you take that limit, which is less than 1. And if our L value, which in this problem is equal to 0, is less than 1, we can say that this is absolute convergent, as listed up above in number 1. And so therefore, the sum from n equals 1 to infinity of negative 2 to the nth power n to the nth is going to be absolutely convergent. And this is by the root test. And also, since it's absolutely convergent, this also means that it's also convergent. The example right below says, find the sum from n equals 1 to infinity of negative 2n over n plus 1 raised to the 5nth power. And so for this problem, our a sub n is equal to negative 2n over n plus 1 to the 5nth power. And again, since this is raised to an nth power, I'm going to consider using that root test first. And so I'm going to look at the absolute value of a sub n, which is going to be the absolute value of negative 2n over n plus 1 to the 5nth power. And I can think of this as the absolute value of positive 2n, n plus 1, since dealing with the absolute values here, to the 5th power, and then moving that nth power outside of the absolute values. So, looking at our limit as n approaches infinity of the nth root of the absolute value of 2n over n plus 1 raised to the 5th power, and then all to the nth power. And so this would simplify to the limit as n approaches infinity of 2n over n plus 1 raised to the 5th power, which is the same thing as the limit as n approaches infinity and putting that exponent to every single term, we would have 2 to the 5th, which is 32, n to the 5th over n plus 1 to the 5th power. So then multiplying both the top and the bottom by that degree in the denominator, which would have been 1 over n to the 5th. And you could multiply out n plus 1 to the 5th power, but realize that it would be n to the 5th, then n to the 4th, and so on, all the way through to 1. And n to the 4th, for say, is going to be n to the 4th over n to the 5th, or 1 over n, which would just go to 0 as you take that limit. And so this would just be equal to, and the numerator would be 32. So 32 over 1, or just 32, which is greater than 1. And since this is our L value, is greater than 1. Looking up above, if L is greater than 1, then we know that the series is going to be divergent. So therefore, the sum from n equals 1 to infinity of negative 2 to the nth over n plus 1 raised to the 5n is divergent by the root test.